Hey guys, welcome back. This is lesson number 5, second day of unit 9. We're almost done. We're almost there. Hope everyone is handling their quarantine okay. Go outside, get some fresh air. Don't stay outside for too long, but go outside, get some fresh air. Do a couple of jumping jacks. Get some sun in your face. It's so nice out today. Right? So today's work that we have due at 11:59 is lesson 5 assignment. There's a brief reading on this topic with questions. I think there's only about 5 questions. Um then there's classwork number 1, which has you using table I and just getting a little bit more familiar with it. The image on classwork number 1 has all the questions on it, and then the rest of the Google form is like writing in the questions. So tell me the delta H and if it's exothermic or endothermic. Classwork number 2 takes place on Test Wizard. That's another 5 questions on basically potential energy diagrams, heat of reactions, and exo and endothermic reactions. So I think me naming this exo and endothermic and not naming it heat of reactions is kind of misleading, but hey, it is what it is. Then we have RLQ2, that is remote learning quiz number 2. This is basically our way of just me assessing if you're understanding what we've been doing it for the next 2 days and seeing how you're going. Homework number 2 is due on Saturday at 11:59. It's been open since Wednesday, so you've had time to look at it and start working on a couple of problems. No, I'm not giving you work for the weekend. I am just giving you the opportunity to finish it and hand it in on Saturday in case you don't finish it today. All right, so relax. Your weekend is for you. On Sunday, I should drop a schedule of what you're going to be doing for Monday, Tuesday, Wednesday, and then on Monday, I should drop what you're doing for Thursday and Friday. All right, so be safe, be healthy. Make sure you have a pencil and a paper next to you so you can take a couple of notes down. I feel like they'll be helpful for this one because I'm going to say a couple of things that might be useful later on. So, this is a quick review of yesterday. I am not going to say it over again. I'm just going to kind of pop it on the screen. If you were a little bit confused of yesterday, I know a couple of people that met us on Zoom were a little bit confused. Go and watch yesterday's video again. It does go into a little bit more detail, or go ahead and make sure you can go back and read that reading again to make sure you get it. That reading was actually really helpful as well. So you can go ahead and look at that for more help from yesterday's video. That was yesterday's video is titled Lesson 4. So we talked about kinetics, the collision theory, and the factors that affect the rate of reaction. And we have nature of reactants, temp, pressure, surface area, concentration, and catalyst, right? Yesterday's explanation goes a little bit more into it. So go ahead and look at lesson 4. It's a really quick lesson, not that long. So it shouldn't take you that long to understand it. All right, so starting for today, one thing you need to remember is that when a reaction is going to completion, we are breaking bonds and we are forming bonds. Now, I said I was going to put this on this, and I guess I forgot again while we started. So let's see if I can write it in so I can give that to you, or at least I can give you the acronym and you can know what I'm talking about. So, when we are breaking bonds, what happens to the energy is that we have this acronym known as BARF, right? And I'll stop right there because I'm not really good at this. But we have this acronym known as BARF. And BARF means that when we break bonds, we are absorbing energy. It takes us a lot of energy to pull those molecules apart, to pull those atoms apart. But when we are forming bonds, we are releasing energy. So when we release energy, the reason why when we're forming bonds, we release energy is because they're coming at each other with such a force that the energy that they're going in with, the moment they impact each other, gets released. Right? So BARF stands for breaking, absorbing energy, breaking bonds, absorb energy, releasing energy forms bonds. Right? So that is what BARF means. I'll put this on the Google Classroom so you have something to refer back to. But when we're releasing and breaking these bonds, we come up what's happening to them. How do we do that? So heat of reaction, delta H, calculates the amount of heat energy lost and gained throughout the reaction. So we know how much energy we're losing and how much energy we're absorbing. So that is going to be our heat of reaction. Now, the thing about heat of reaction is that they use heat of reaction and entropy interchangeably. So sometimes they might like calculate the heat of reaction, or sometimes they might be like, what is the entropy? Same thing. You're still dealing with delta H and you're still calculating the amount of energy lost or gained. Now, how do you calculate the amount of energy lost or gained? Easily. You're going to subtract the potential energy of the products from the potential energy of the reactants. I'm going to say that again. You're going to subtract the potential energy of the products from the potential energy of the reactants. Once you subtract those two values, you will have your heat of reaction or your entropy. Now, sometimes you might need to be able to calculate it, and that's where the potential energy diagram comes in handy. And I'll show you that later on. But sometimes you might not need to be able to calculate it. You might just have to look at a table, and that's table I. Now, before we look at table I, you need to understand what you're going to be seeing. So on table I, you're going to see the reactions, and you're going to see the heat of reactions. And some of the numbers are positive and negative. What do they mean? Well, these are when these two reactions come into play. So these two reactions are going to help you determine what that is. So when you've lost energy, you're going through an exothermic reaction. This is how you have a negative delta H. And then when you gain energy, you have an endothermic reaction. That's when you have a positive delta H. Now, do you see how over here it starts with an X and over here it starts with the endo? Because energy is going to exit and endo energy is going to enter. I'm trying so hard with this. Oh, that's something. All right. So when we have an exothermic reaction, our energy is going to exit. Exo meaning exit itself, thermic meaning heat. So heat is exiting. Endo meaning enter, thermic being heat again. So heat is entering. Now when energy is exiting, it's going to exit from the product side. Right? Let me see here. It's going to exit from the product side. And then when energy is entering a reaction, it's going to enter from the reactant side. Right. I think I'm going to stop right here. Actually, let me continue. Right? It's going to enter from the reactant side. So sometimes I'm like, how do you know that this is an exothermic reaction? I know it's an exothermic reaction because my energy, which could be in a number form, or it could just say energy or heat, is on my product side. Or I could say I know it's an endothermic reaction because my number form, or my heat or my energy is on my left side, my reactant side. Also, I can tell because it has a negative delta H, which makes it exothermic, or positive delta H, which makes it endothermic. Now, one thing I wanted to say is whatever happens to your reaction will happen to your delta H. So if your reaction is doubled, your delta H will also be doubled. If your delta H is divided in half or cut in half, your reaction is also cut in half, right? So maybe instead of you starting with 2 HCl, now you're starting with 4 HCl. That means that your delta H for that HCl is also doubled, right? Same thing. They work as coincide. So they work together. Coincide, I don't know what I was trying to say. Right? So like I said, sometimes you might not need to calculate delta H. You just have to look on table I. So at this point, I'm going to put this practice problems here. You can pause it right here and go ahead and use table I to answer these questions. And then we'll meet back up. So pause it now. All right, so if you're back, then you've paused it and you've figured out your answers. So for number one, our delta H is in kilojoules, which is going to be plus 66.4, making that a endothermic reaction. Brilliant. Now, number two, our delta H is negative 91.8, making this an exothermic reaction. Great. Now, some of you are probably having problems with the last one. Perfectly fine. The last one, right? The last one is number two, but backwards. It's been flipped. So because it's been flipped, our delta H will also be flipped. So instead of our delta H being negative 91.8, it is now positive 91.8. And instead of it being an exothermic reaction now, it is now a endothermic reaction. If you go on the Google Classroom, there are a couple of more practice problems that work with table I. Go ahead and get a little bit more familiar with that. All right. So as we move along, like I said, we have this potential energy diagram. Now, this potential energy diagram tells us how much energy we're going to be using throughout the reaction. Now, one thing I just want to say is the reaction does not go to completion until we pass this hump. If we have not gone over the hump, the reaction is not starting yet. Once we go over the hump, that's when the reaction starts. Now, so let's first label this graph. So over here, we have our reactants in the beginning. At the end, we would obviously have our products. Now on the top, our hump, we have our activation energy, the energy needed to activate. If we cannot, that's the energy needed for us to go to completion. Now, this graph can also help us calculate delta H, our entropy, our heat of reaction, because it's giving us the potential value, the potential energy value of reactants and products. So the space between those two would be our heat of reaction, our delta H, our entropy. And all we would need to do is subtract these two values together to get our delta H. Now, sometimes the Regents questions don't even ask you to subtract. They just want you to know which arrow would represent that value. So it would be the space between the products and the reactants. Now, as we can see this dotted line right here, that is our catalyst. Now, our catalyst, like I said yesterday, lowers our activation energy by providing an alternative pathway. So our catalyst is not changing our reactants or our products. It's just causing the hump to be lower. And by making the hump lower, we now have a shortcut to get to our products. It's not changing the products, it's not changing the reactants, it's just taking less time. So, because we're dealing with potential energy diagrams, we're dealing with exo and endothermic reaction, they each have their own potential energy diagrams, but those three components are still the same. So our exothermic reaction, we're going to lose energy, so we're going to be lowered down on the potential energy part. We've lost energy, so our potential energy is a little bit lower. For endothermic, we've gained energy, so our potential energy is going to be a little bit higher, right? But the same, we still have the reactants, we still have the activation energy, and we still have the products, right? What is forward and reverse? The reason why I'm giving you forward and reverse is because some of the problems that you're going to be dealing with, some of the Regents-based problems, are going to tell you, oh, what is the forward reaction or what is the reverse reaction? Very simple. So the forward reaction is when we're moving from our reactants to our products. So when we go from A to C or AB to C, right? The reverse reaction obviously would be the reverse of that. So the reverse reaction is when we go from products to reactants. We have the same reaction, but we're moving in the opposite direction. So we're going from C to AB, right? That is what the forward and the reverse reaction is. Now we have a little bit of time left, so let's do two practice problems here. Probably only get to one. So for number 6, it says which arrow represents the potential energy of our reactants. Well, first thing I want you to do is I want you to label each part of the graph. So we know that this is our reactants, we know that this is our product, and we know that this is our activation energy. Now, it says it only wants the arrow that represents the potential energy of the reactant. So it only wants the arrow on our reactant side. So we have B and A. C and D are not important. But A is giving us A is giving us the reactants and the activation energy. We don't want that. So our answer is going to be B. Go ahead and solve for 7 and let me know in the comments what number 7 is. If you need any assistance, just let me know and have a great day, guys.